27th of 2016 of October, and this is where we left off yesterday. We had gone from that Dalton model, just the big sphere, up through Thomson's model, that plum pudding model with the dispersed negative charges. Rutherford introduces the planetary, and Bohr improves on it. And the big thing that Bohr says, coming out of hydrogen line emission spectra, coming out of the idea that, light and matter both behave in in quantum ways, that there are discrete amounts of energy. He says, no, you know what, there are orbits. And be very careful with your terminology here. These are not orbitals. What Bohr proposes are not orbitals. People want to call them that. They're not. They're orbits. In Bohr's model, those electrons are orbiting the nucleus in prescribed fixed paths. Those are not orbitals. We're getting there. So this is where we left off. Now, there are still some problems with this model. And the biggest problem is, it is beautiful when you only consider hydrogen. When you get up into larger elements, which is everything, because hydrogen is the lightest known atom, it doesn't work so well. So it was understood that this was sort of a stopgap explanation. There was something missing from this. And this is where Louis de Broglie's ideas come in. So de Broglie was actually French minor nobility. He was the second son of a noble family, and in the models of inheritance in most of European nobility, and he was French. The second son gets nothing. The first son gets everything, and the second son has to make a way for himself in the world. And the daughters get nothing. They just have to marry well. It's really a bum deal for everybody but the eldest. So de Broglie was a minor nobility and a particle physicist. It was known based on Schrodinger's work, or not Schrodinger, I'm sorry, Planck's work, that light behaved as a wave. Well, so Planck says light can behave as a particle, or energy can behave as particles. So Planck says energy behaves as a particle. Einstein then says, aha, light behaves as a particle. Light's a form of energy. De Broglie comes along and says, well, if energy can behave as a particle, then matter can behave as a wave. Oh. Well, that's a weird little twist on things. And what he does is he imagines electrons behaving as waves of very specific frequencies all around the nucleus. And if you remember when we talked about wave behavior, we said that there was a relationship between energy and frequency. That frequency and energy were related. Well, what he says is the amount of energy in each of those electrons based on Bohr's model actually gives it a frequency, and frequencies are a feature of waves. Now, I would like to invite you to blow at least 30 seconds doing the following. Look at your hands. So de Broglie, I think this was actually what he proposed as his doctoral thesis. He handed it to his advisor, who said, I don't understand this well enough to even comment. Why don't you send it to Einstein? And Einstein took the paper and said, yeah, I think you got something here, kid. And you know, that ends up being de Broglie's big contribution, that electrons can actually behave as waves as well as particles. So if they have frequencies, if they are waves, there are some other things that we can then do. About the same time, we have these two men working sort of at odds with one another. They actually had rather a big feud. So this is Werner Heisenberg, German particle physicist. This is Ernst Schrodinger, another German particle physicist. They were working towards the same stuff in opposite directions. And what Schrodinger did, we'll talk about him first despite the fact that he's second on the slide, is he said, well, if that electron is a wave, I can find an equation for any wave. How many of you have had to manually graph a sine wave? How many of you have seen the graph of a sine wave? How many of you have graphed anything in your lives? Thank you. From an equation. You know that there's an equation to describe every line. If I say x equals y, I get that. Whoops, I get that. Straight line. You know, what he did was work from the fact that electrons were behaving as waves, as proposed by de Broglie, and create equations for them. Now, what was interesting, because remember, Bohr says they have a certain amount of energy, de Broglie says they have a certain frequency. What Schrodinger says is, well, when I create an equation for the wave, there are only certain numbers that will allow the equation to be solved, which means that there are a limited number of possibilities for those electrons. At about the same time, what Heisenberg is doing, and Heisenberg is a fantastic theoretical physicist. He's a lousy experimentalist. I'll tell you a funny story about that a little bit later. He proposes that you can't actually know both the position and velocity of an electron. That the act of observing the electron changes its either position or velocity. So at the same time that Schrodinger is coming up with these equations, Heisenberg's saying you can't actually pin these things down. Well, it turns out, if we look at Schrodinger's equations, you have done equations for two-dimensional lines, right? They have an x and a y component. Schrodinger's equations are three-dimensional. They have an x, a y, and a z component. The z-axis is the one that comes right back at you. Schrodinger's equations describe three-dimensional spaces, and I'm doing my best to make that clear that that's three-dimensional. What his work paired with Heisenberg's work means is we can't pin down where it is, but we can give you an area of high probability of where it is. Coming out, oh, it's freezing again. Okay, so what we get out of the work of, starting with Planck, going through Einstein, ending up with de Broglie, what Heisenberg and Schrodinger did with de Broglie's work, and building on the basis of that old Bohr model, is we get the quantum model. And the quantum model says that there is a dense central nucleus, it's got protons and neutrons. That much has not changed. It says that electrons are in specific areas outside the nucleus. We get rid of that idea of nice little racetrack lanes around the nucleus, and that they're constantly in motion, that they don't stop. The thing that remains from the Rutherford planetary model and the improved Bohr planetary model is that idea of main energy levels. And we'll look a lot more at how those sort of factor as we go. This is a further description of this quantum model. We don't know where the electrons are exactly. That comes out of Heisenberg. But when we look at values that will allow solutions to Schrodinger's wave equations, what we get are three-dimensional areas where there is a very high probability of there being an electron. Those areas of high probability are what are called orbitals. They are not orbits, different things. And when we smash all the orbitals together around that little dense nucleus, we get this giant fuzzy cloud. It's called the Electron Cloud that surrounds all atoms. I like to think of it as a BB embedded in about a half a meter of cotton candy. So it's a tiny, tiny, tiny dense nucleus surrounded by, oh, we should make a model with cotton candy. That'd be a great idea. BB's in the middle, but people might break their teeth, and that would be bad. Surrounded by this big fuzzy cloud, and that's where the electrons are. And within that fuzzy cloud, of course, there are different regions where different electrons are allowed to live, and they can't. If they hop up, they have to take in energy, and if they fall back, of course, they give off energy in the form of light. But that's kind of what we know now. So when we look at these models, the development of these models, we go from Dalton to Thomson to Rutherford to Bohr to this sort of new quantum model, which is really hard to see there. The question that people want to ask is, which model is correct? But in science, models don't necessarily work that way. So in this case, specifically with the last two models that we talk about, the Bohr planetary and the quantum, they're each useful. And remember, they are just a description of our understanding of something. So we use them both. When I said the Bohr planetary model is what you used in physical science when we were learning energy levels, and there are 2 electrons on the first energy level, and there are 8 on the second. You're going to understand why that is as we start to look at the quantum model, because now we're going to really examine orbitals. In chemistry, you're learning a more complicated, more complex understanding of what you knew in a simple form. Yay! We use both of those models. We don't use the Dalton. Well, do we use the Dalton model? In a way. I mean, when we talk about atoms are vibrating, the very first kind of model that we give kids when you start to learn about atoms in the elementary level. What are they? They're little tiny pieces that make up the whole world, and that's all we talk about. That's basically the Dalton model. They're little tiny pieces. So it's interesting. There's kind of a parallel progression with what you learn as a kid up to your more complicated understanding as chemistry students, that you've kind of walked through those models. We don't really, plum pudding I guess is kind of useless, but you do use that very simplified solid state atom kind of thing. And then, we move up through now, we have some more complexity. But anyway, that's it.